In a darkened shipyard, a giant steel portion of a colossal container vessel, stretching longer than a football field, stands silently. It sits within a cavernous assembly bay, surrounded by massive cranes poised to lift enormous sections, each weighing up to 600 tons, into place. This leviathan of the seas, known as an ultra-large container vessel, or ULCV, represents the peak of human engineering. Yet, crucially, it's not merely constructed as a single piece. Instead, it is meticulously crafted in segments scattered across vast distances. Today, we unravel the enigma: why are megaships built in sections miles apart before being precision-joined in a final assembly? As we explore this question, consider the sheer scale of what we are discussing. A single ULCV reaches deadweight tonnage exceeding 200,000 tons, a size that brings unique engineering challenges. And as strange as it may seem, traditional construction methods, where ships are built from the keel up in a linear fashion, simply do not apply to these massive behemoths of the sea. To grasp the necessity of modular construction, we must first understand the immense stresses these ships endure during their operational lives. At sea, heavy seas can impose structural loads that are staggering. When a ship encounters waves, the force acting on its hull can exceed thousands of tons per square meter, presenting a tremendous challenge for engineers. Imagine a brake pad the size of a house trying to stop a freight train rolling downhill. This metaphor offers a glimpse into the physical forces at play. The weight of the ship combined with the dynamics of ocean movement creates forces that must be managed with precision. Each hull section is engineered to withstand these enormous pressures, which is why they are constructed separately rather than being built as one continuous piece. Historically, one can look at the Maersk Triple-E class, one of the largest container ships ever built, which has a capacity of up to 18,000 20-foot equivalent units. The Triple-E stretches over 400 meters in length and stands over 60 meters tall at its highest point, presenting a unique set of challenges. Its design requires a careful balance of buoyancy, weight distribution, and structural integrity to ensure it can both sail efficiently and endure harsh conditions. By constructing it in modular sections, engineers can optimize each block for the specific stresses it will confront rather than compromising the entire vessel's design. Common sense might suggest that building a ship from a solid keel would provide better structural integrity. However, the opposite is true for these vessels of immense size. The modular construction technique allows for assembly in multiple locations, often referred to as shipbuilding hubs. This decentralization not only speeds up the construction process by enabling simultaneous work on different sections, but it also alleviates congestion in shipyards prone to delays. Engineers have learned that these large sections can be best aligned and integrated during the final assembly phase. Using laser alignment systems, workers can ensure that each section is precisely positioned within tolerances of under 3 mm. This high degree of accuracy is indispensable. If the sections were to misalign even slightly, the ship's watertight integrity could be compromised, leading to disastrous consequences. Now consider the intricate maze of energy and structural loads during operation. Each segment of the ship has specific roles, some serve as cargo holds, others as engine rooms or living quarters for the crew. As such, they are designed using advanced computational modeling to predict how various forces interact within the ship. For example, engineers utilize finite element analysis to understand how hull shapes distribute stress loads, which helps dictate the size and shape of individual segments. Before joining, engineers will benchmark the ship's performance against simulations that account for everything from high winds to wave activity. This calculation is not merely academic. During tests, actual ULCVs must withstand forces well beyond what any average ship would encounter. The United Nations estimates that about 90% of the world's trade is carried by sea, and as such, these vessels must be resilient. They become floating fortresses, designed to endure the harsh realities of maritime life. Now, take a moment to engage deeply. Which of these machines would you least want to be standing next to when it is in operation? The ship you've just learned about, the towering cranes that assemble it, or the powerful tugboats that guide it to port? Let us know your thoughts below. Returning to the construction methods, one might assume that the larger and heavier the vessel, the fewer limits it would have on construction methods. Strikingly, the facts reveal the opposite. Some may believe that heavy machinery could be simply built up from a foundational layer. However, practical engineering dictates that separating construction from assembly offers flexibility and accuracy impossible in traditional methods. Each section is designed with its own structural specifics, allowing engineers to tailor each block's integrity to different operational functions and positional stresses. A hull block, for instance, will need to accommodate the immense weight of cargo and wave stress differently than a deckhouse designed mainly for aerodynamics and living quarters. This specialized design minimizes material usage while maximizing safety and efficiency. Another example can be found in the construction processes of the APL England, a container ship that suffered a structural failure due to improper load distribution during transit. Engineers quickly realized that the collective loads from both the cargo and structural shifts from the sea necessitated a re-evaluation of traditional construction practices. Now, modular construction methods have firmly taken root within the industry, demonstrated by the ongoing development of the new generation of megaships. So, what is the actual trick behind building a vessel that seems impractically colossal? It lies not just in the construction methods but in redefining how we conceptualize assemblage and maritime engineering. When a ULCV slides into the water, it is the result of a complex dance of modular design and precision assembly. Each segment, built hundreds of miles apart, is designed to fit together with an accuracy that is nothing short of extraordinary. In conclusion, the engineering feats surrounding the construction of megaships illustrate the remarkable ingenuity we can achieve through adaptation and foresight. As we transition deeper into the age of superstructures and increasing global trade demands, our understanding of these technologies becomes invaluable. It serves as a testament to the hidden engineering that surrounds us, where the ordinary often conceals a view into the extraordinary realm of human capability and innovation. The machines that move the modern world are stranger than they look. Subscribe, and we will take apart the next giant together. To delve deeper into the mechanics of construction and assembly, we must recognize that each segment of a megavessel serves specific functions and must withstand distinct loads throughout its operational life. The tolerances required when aligning and joining these components are astonishing. For instance, the precision required for the final join can be likened to the meticulous fit of puzzle pieces. One erroneous dimension could lead to cascading failures down the line. In a traditional shipbuilding method, each ship would rise from its keel, one layer upon another, potentially leading to misalignments due to thermal expansion, structural settling, or even minute imperfections in the foundational layers. However, consider modern adaptability. Having assembly sites spread across varying regions allows for locally sourced materials and specialized skills for different sections. For instance, the hull may be constructed in one part of the world, while the cargo holds might be built in another facility with a focus on specific construction techniques best suited for materials handling. One extraordinary case is the construction of the HMM Algeciras, launched in 2020 and currently one of the largest container ships in the world, with a capacity of over 23,000 20-foot equivalent units. Rather than traditional methods, its segments were developed and assembled in China, where shipbuilding infrastructure has been optimized for efficient modular construction. The strategy not only reduces risk but also mirrors supply chains for materials, leading to greater cost-effectiveness as well as reducing lead times. Courageous innovations in shipbuilding have also led to the adoption of sustainable practices. For instance, engineers are now examining the potential for construction from composite materials rather than traditional steel, which can weigh less and reduce energy consumption during transportation. Yet, while composites provide potential weight reductions, one must also account for their behavior under stress. This aspect exemplifies why engineers use simulations extensively. Separate modules can be tested to failure to determine their breaking points without risking the loss of an entire vessel. When it comes to the assembly process, precision is paramount. Laser alignment systems represent a cutting-edge technique for achieving the millimeter-level accuracy required in final assemblage. The technology can establish reference points across several hundred meters and utilizes intersecting beams of light to evaluate physical deviations. This meticulous approach ensures that even segments constructed in different environments and under different conditions can join together seamlessly, creating a hull that remains resistant to environmental forces. Remarkably, before any segment is deemed ready for final assembly, each section undergoes rigorous testing. One of the critical examinations is hydrostatic testing, where sections are filled with water to assess integrity under load. An awareness of every detail, right down to tolerance and fit, allows engineers to catch potentially catastrophic issues that could arise once the ship is in motion. Another essential component of this process is the dunnage system. Often employed during cargo operations, dunnage consists of airbags or pads specifically designed to fill empty spaces in the hull, providing stability and support that protects the overall structure from shifting loads. As megavessels can hold vast quantities of varying cargo weights, this system is vital for maintaining equilibrium during transit, especially during adverse weather conditions. We have also observed the increasing requirements for thermal and acoustic insulation in the design of these vessels. Take, for instance, the incorporation of sound-dampening materials that minimize noise pollution in marine environments, which present increasingly stringent regulations around noise levels. This focus leads to engineers selecting materials that don't warp or deteriorate under the thermal stress from both the sun and the sea, showcasing again the need for tailored design upon individual blocks. Throughout this exploration, we must continually acknowledge why modular methods have revolutionized shipbuilding and resolved common pitfalls. Extensive case studies have demonstrated how modular sections possess superior structural resilience. For instance, the Galaxy class of cruise ships, originally constructed in the proposed traditional method, suffered a significant failure while at sea due to overhangs exceeding safe structural limits. This led to a subsequent shift toward prefabrication methodologies prevalent in modern designs. Engaging with the technology embedded in these construction methods, one cannot overlook the advances in robotics and automation that facilitate the construction process. Robotic welders, capable of executing millions of precise welds with perfect timing, significantly reduce labor hours while improving the quality of welds, essential for maintaining hull integrity under extreme loads. Moreover, augmented intelligence helps engineers identify anomalies in the data flowing from sensors that monitor stress levels and structural integrity throughout the lifecycle of a vessel, allowing for preventative maintenance based on real-time information. Imagine the task of aligning a hull section with the precision of a paper-thin filament inserted into a circuit board. Envision the complexity involved in ensuring that 1,000 tons of steel fit together perfectly, ready to withstand storms that generate waves over 20 meters high. Such challenges demand an engineering mindset flexible enough to adapt, innovate, and learn from failures. Reflecting on the scale of these projects, it is essential to understand the collaborative nature of modern shipbuilding. In the global ecosystem of manufacturing, the construction of a ULCV leases local economies in shipyards and material suppliers while pulling together skills across disciplines. Engineers, environmental scientists, and specialized labor come together as cohesive teams. This broad collaboration gives rise to ships that not only serve the commercial market but also take into consideration ecological impacts, operational efficiency, and pioneering technology. So, at its core, why are megaships constructed in sections miles apart? The answer lies not just in efficiency but in an evolution of our understanding of engineering forces, structural integrity, and the necessity for greatness to be simple yet effective. Each section built with its unique requirements, poised to fit together flawlessly while handling challenges posed by nature itself, this creates not just a work of engineering art but a testament to interdependence within human ingenuity. As we contemplate the future of shipbuilding, the importance of innovation continues to reign supreme, which raises a poignant question: what might the next generation of mega vessels look like? They may well embrace even more advanced materials, autonomous pilots, or even designs that enhance a vessel's energy efficiency through innovations in hybrid power systems. In a world where shipping continues to drive global commerce, understanding the underlying mechanisms that enable these colossal vehicles to operate seamlessly provides critical insight into the broader narrative of modern engineering. Our inquiry into why megaships are built in sections scattered over miles emphasizes not only a technical necessity but the very essence of creativity and adaptability that defines humanity's approach to engineering challenges. The machines that move the modern world are stranger than they look.